the confidence interval is basically a number. It's number. It's like something like 24 plus minus something something something. So that is uh, for example, let's say I put something like this, 70 plus minus 5. So the confidence interval is basically 70 65 to the what we call to the 75. So that's basically what does it mean by the number. So the middle here, this number here is basically the average, the average, and then this 5 here is basically the standard error lah. So the 5 here is this 5 is basically the standard error. Okay, if you look at the what we call this thing, the table here, you can see Ci x bar plus minus you have T times Se. Okay, so let me put here confidence interval equivalent to x plus minus, and then you have T. Let me put in the different color T, and then let me put different color also x, and then you times with the Se. So Se here stand for standard error. Standard error here is basically Se equivalent to S over this N. Okay, so where this S is basically the standard deviation. This is standard deviation. Okay, so that's standard error. So the value T here is coming from T distribution. Okay, the X here is basically the mean, the average lah, the mean lah, the mean of your sample. One thing about the confidence interval is that you only use confidence interval for when you do sampling. Okay, because if let's say you don't do sampling, you test the population, then there are no confidence interval because you already confident that whatever you say is true. But when you do sampling, for example, this is the population, let's say population, this is population, and then you have this sample, you have 4 sample, when you do this thing, when you perform your analysis and so on, statistical analysis, the idea is that you want whatever you say about your sample representative of the population. The aim is basically you want, this is the aim of statistic lah. You want whatever you said, whatever you got for your sample, meaning that the standard deviation, the standard error, the standard like standard deviation, the mean and so on, relate to the representative population. Relate to population. So that is the reason why you have the confidence interval. That's why you have standard deviation. You know, the what we call the symbol is sigma. So the idea is that this sigma, whatever this sigma of the sample, you want in such a way that that sigma also represent the true population. So that's the idea lah. If you have population, so and also when you have this thing, you are not confident yet. But the problem here, even though you said you want this sigma to be sort of like representative of the sigma of the what we call of the population, you want that, but in reality you are not sure. You are not totally sure. You're not what we call 100% sure about this thing. So that's why comes the confidence interval. So that's one case lah. So let me make it smaller. So let me make it smaller here. Make it smaller. Okay. So that's one the reason. But if you have a population alone, let's say if you have a population, the entire population of Malaysia, for example, let's say you know every single individual, you can count every single individual in Malaysia, then your what we call whatever you get here, whatever you get is true lah. It's true already because you already take into account everybody. So in this case, your what we call your sigma, your standard deviation of population is basically true lah. Is because you already consider everybody. So in this case, when you are already confirmed about everything, you already check every single individual, then you have nothing to do with the confidence interval. You already 100% confidence. So there are no confidence interval when you talking about population. So that is two reason why you find the confidence interval. This is, let's say I put like this. So this is, so let me put like that lah. Let me put like this. Okay. So that's why in this what we call statistic table, there are no confidence interval for population. Okay, so here there are some mistake a little bit lah. This is S actually, okay, because it's coming from the top. This coming from the top, so it's not this mistake here. This S here, this S Here, for example, standard error, you still can find for what you call for population. You just sim lah, SE equal to sigma over square root n. So you can still calculate standard error for the what you call for the population. You can still find the standard error for the sample. The standard error here that you find for your sample is basically the estimate. You want to estimate the population standard error. So that's the difference. Standard error in here, in what we call in population, is real standard error lah. The confidence interval, like I said, you only see on the sample because you want to see how confident whatever you get relate to the population. And normally, this is what you do when you perform DOE. Because when you perform DOE, you are taking just a few things, and then you want that few experiment that you do represent other experiment. Let's say you what call in the experiment mentality is like this. From the experiment viewpoint, why this is matter is that this is like this. Let's say you do the experiment because maybe it's not clear for you why we want to talk about sample population and with the DOE. So the idea is this: when you deal with the experiment, let's say you have the experiment, you want to see the average of the, let's say you have this, let's say I make example, you have a dice, okay, you have a dice, and then let's say you have two dice, you have two dice, you throw the dice, this is your experiment, you throw the dice 50 times. Let's say you throw 50 times. So when you do this experiment, you will get what? You will get all the stuff lah. You will get mean, you will get standard deviation, and also on lah. So that's one experiment. So let's say you get what you call the mean. Let's say the number that you get when you roll two dice, the maximum number that you will get is 12, right? Because 6 you get 12. So let's say the mean, let's say you get around whenever you throw the dice, whenever you throw two dice together, because this I want to relate how this population and the population and sample in the experiment term. Because if I say like this, it's more like the data from observation, but now how to relate this, how people use this confidence interval in the experiment. Okay, so let's say you have two dice, so you know the minimum that you will get is 1 plus 1, meaning that when you roll two dice, each dice the lowest number is 1, so the minimum for two dice is 2 lah, is 2, the count is 2. The maximum if you roll two dice will be 6 plus 6 equal to 12. Okay, so far so good. So you throw two dice, and then you throw it 50 times. When you try to tabulate all the data, so you get something like this. Let's say this is a number of the number you got, number you got lah. I mean the result lah. We say this is the result. So this what we call result. And then this maybe they are 50 times lah, from 1 into 50 lah, from 1 2 3 until 50, like that. So if let's say you try to find all the frequency, you will see that to get these two is so difficult. To get 12 is so difficult. But you can get a lot in the middle, because for example if this is the result 2 and 12 is the extreme, we say. But in order to get, let's say 5, let's say if for number 5, to get 5, to get result of 5, meaning that the value 5, you can have few combination. The first combination is 4 1, 4 plus 1. The second combination is that another dice is 1 plus 4, and then the A pula. The first combination this, the second combination is that. The third combination you can get 3 plus 2. The fourth combination is 2 plus 3. And then what else? 3 2 2. Yeah, 4 1 1 2 3. Yeah, there are 4 combination lah kan. 4 1 4 1 2 2 2 3 3. Yeah, that's the combination lah. So you have 4 times combination. So it's more likely to get, so meaning that it's you got 4 combination to reach result 5, meaning that you have 4 combination. Compared to this you only have one combination. One combination. Either both dice must be 1. Here both dice must be 6. Only one combination. So when you try to plot, when you try to scatter all the possible result, that's why you will get something like this thing. So this is not number lah, because so this is a number. Let's say this, put the number lah. Let's say this number 1 2 3. This one like this. This is frequency lah. Frequency 4 5 6 7 8 6 until 16 lah, until 16 pula, until 12 lah, until 12, because you have only 2 dice. So you will see most of the value will be in the middle. That's why you got this thing, what we call the bell curve, because you get more combination to reach this middle. Okay, so the middle is around 7 lah, 7 6 or 7, like that lah. So that's this, if let's say, okay, so that is the experiment that you perform. So when you do this experiment, you can find few things. You can find the mu, you can find this mu, you can find the what we call the average. You can find also the what we call the standard deviation, and that's the 2 main thing lah. So now let's say now you want to, so now this is better, you confused. So this I think I better put like this, mu here, and then I put standard deviation here. Or better I draw like this, standard deviation lah, standard deviation. Okay, so you get this mu and standard deviation. So now let's say you want to repeat this experiment. You want to repeat experiment many times. So let's say you want to repeat the same experiment many other times. many other times. Okay, say you want to repeat this experiment many other times. So this from the perspective of you doing the experiment is like you want other person repeat. From the perspective of doing experiment in the lab, it's like you want whatever you got, you want if other person repeat exactly the same that you what you do, you will at least whatever result that you get, whatever this thing, whatever result from you get here, the mu and also the mu and also signal the standard deviation reflect, they will also get almost similar with what you get. So that's why comes the term standard error and also confidence interval and so on. Because now when you do alone, for example in this case, in this experiment, this one experiment is one experiment only. But then you want, if other person repeat your experiment, then your experiment becomes sample. If let's say in this world, you are the only one performing this experiment, so meaning that you are the population, your experiment, the 50 times you you roll the dice, that is the population lah, 50. But if let's say hundreds, thousands of people performing the same experiment, then your experiment, your one experiment is becoming the sample of the entire population. So that's how you relate the sampling and the population with regard to an experiment. So in other words, you want your result will be the other person, if they repeat your experiment, will be getting what you get. So that's the idea with this sampling and population lah, how to relate this sampling and population in the field of doing experiment. If not, if I say just like this, population and sample is quite not clear lah. How come my experiment have population and sample? So this is the way lah. So you want whatever you estimate here, so is basically represent the ni lah, the others who perform the same experiment again and again. Okay, so if you see at this confidence interval, you see something. You see this T. Okay, so this T. The T there is basically, let me put something like this. Okay, so the T relate to something. T is T value lah, is relate to T distribution. T distribution. When you talk about the population, normally we deal with this thing, like we deal with what we call the normal curve. Okay, so this is what we call this thing. So you see, when you deal with the population, you have this what we call the standard normal curve. Standard normal curve. Okay, you get this standard normal curve for the population. Let's say this is a population. Let's say this is a population. You get this curve. Okay, when you perform your experiment, let's say you perform your experiment like this dice, you also have the curve, but this curve will not be exactly the same as standard normal curve. Okay, your curve, let's say this is your curve, this population, let's say this is your sample, your curve will be same, but it's not exactly the same. So that's the thing. Maybe your curve will be like flatter like this and so on. Okay, so this is maybe your curve lah, your sample curve, Okay, so in order to relate this curve to the normal curve, standard normal curve, you need to do some conversion lah. Because the reason why you want to convert your curve, for example this thing, you want to convert this thing to the standard, this thing to this what we call, to this part, the standard normal curve, is because as we learned before, when you have standard normal curve, you can find the probability. We learned before here in the last class, when you have this standard normal curve, standard normal distribution, the mu at 0 and this the standard deviation is 1. If you can relate your curve with this, then you can find the what we call the probability, and this probability is basically the confidence lah, how much confidence with your experiment. So that is the p-value and so on. whether your experiment result, whether the null hypothesis is accepted or not, how much confidence you are to that. So that is basically there. That's basically the reason. But here, when you have this thing, you don't have what we call whenever. So this, like your experiment. Let's say this is your experiment. Your experiment. If you try to superimpose these two graph, you will get something like this. If I try to superimpose this graph, you get something like this. Something like this. Let's say the red one is, let me draw very clear. This thing. Let's say the red one is the, okay, let's say the red one, this is a normal. The red one is, let's say this is a standard standard normal distribution. If you try to what we call to interpose, your graph might be something like this. So for that case, I've used blue. So let me change this as blue lah. So at least it's not confused. Okay. Okay. So when you interpose, you get something like this. So when you have graph, the blue graph here. So this is the blue graph. This is your your distribution lah. Your distribution. It's normal. It look like normal, but it's not exactly same as a normal standard deviation. So because it's not exactly distribution, because it's not exactly equal, then you cannot just straight away use the table, the Z table, distribution table. Okay, this happened because you are doing with the sample. This blue thing is not exactly the same as the standard normal distribution because you are dealing with the sample. You are not doing the population. You are doing with the sample. That's why it's lower. Okay, one thing about T, the T part here, this T thing here is basically the what we call when you have the T value. Let me put the T there is basically the idea for T is this: if you have higher what we call higher degree of what we call higher let me do like this lah. So this is so basically when you T tu ni lah, your distribution we call it T distribution lah. T distribution. Okay, T distribution, because you are not working with the population. The standard normal distribution is basically we call it also Z distribution. Okay, so if you look at the statistic table here, when you see here, when you see the table, you can see standard normal distribution. This table, the one that we see, that where you can find the area of probability, is basically the Z distribution. We call it Z lah because you can see here Z, right? Z. We call it Z distribution. It's basically when you're dealing with the population, or when you know, or when you dealing with the when you know the population lah. But when you don't know the population, you are dealing with T distribution there. But there are no T distribution table. You have critical value for T, but there are no T table here. There are no T table. If you go to any statistic book, there are no T table. You only have Z table, Z distribution table. So, but you know that when you have this thing, you can find the area. But here you cannot find the area. Here for T distribution, you cannot find the area. So this T distribution will be closer and closer if you increase the degree of freedom. Okay, so this T distribution. So let me draw something like this. Imagine this thing is your normal. This is your normal distribution. Your T distribution, let's say I take blue. So this, okay. So let's say this is degree of freedom around let's say 5. Let's say 5 lah. What does it mean by degree of freedom? We learned before degree of freedom is what? Degree of freedom is basically n minus 1 lah. Meaning that your sample lah. Meaning that your sample size is 6 lah in this case. You have what we call sample size is what we call 6 lah here. But if you try to increase the degree of freedom, you see the tail here. This is the tail. The tail, it become lower, and then the peak become higher. Sorry, I need to take this call for a while. No? Saya tengah workshop ni. Saya tengah kasih workshop. Nanti boleh nantilah. Okay. 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 Okay, sorry for that. Okay, sorry for that. Okay, so we continue. So you can see the when you increase, so the green one. So let me put the green one is degree of freedom. Let's say 10 lah. Let's say 10. Let's say 10. Let me put here degree of freedom. Degree of freedom equal to 10. This discussion might be feel dry, but later it's quite important also lah, because at least you know what you're dealing when you doing the DOE. Okay. So you see there, the more you can see here, the higher the sample size, the closer your distribution, which is the T lah, distribution or T distribution to normal distribution. So that's the reason why you, if possible, do as much possible run. Okay, because of this reason. If not, whatever you relate not really correlate with the actual population. Imagine the normal distribution, the red one is actual population. So you do sampling, and you want that sampling representing the population. If you do with lower number of run or experiment, whatever you get will not represent the population. So in order to represent the population, you have to increase the sample size. And the reason why you need to increase the sample size is this. Is because you want to make sure your T distribution closer and closer to the normal distribution. So that's the idea. Okay. If let's say, for example, I give example. Let's say example. Let's say you have confidence interval or CI equal to 95%. So if let's say you want to find no, it's not confidence interval, not confidence interval. If let's say your confidence level equal to 95%. Okay, and then you can find your confidence interval by x plus minus the T times SE, the standard error. Okay, so if let's say your what we call your if you know the population, if you know the what we call this, because if you look here, the T, let me see statistic here. Where is the thing? Okay, if you look here, the standard error. If you are doing with the sample, you have what? You have the S. If you standard error for the population, you have the sigma, the standard deviation. S and sigma is basically standard deviation. If let's say you know the population standard deviation, for example, if you know the population standard variation, Okay, if you know the standard, the population standard deviation, okay, let's say you know the population standard deviation. Balik lah. If you know the population standard deviation, then you don't need to deal with T. Okay, as we talked before, T, you deal with T if you are doing sampling. You deal with T, you don't so you don't need to care about T lah, about T, because you T, remember the concept of T is that is a sampling. For the sampling, when you do sampling, you use T distribution, but now you already know the standard deviation of the population, so meaning that you are dealing with the population. So when this happen, you will got confident interval, even though I said before there are no confident interval for the population, but just you already confident actually, but you can just to put it CI equal to X plus minus you can get here what 1.69 SE. Okay, let me explain this thing, why they are 1.69 here, why they are this thing 1.69. Okay, see our example. What we look at this example, let me draw like this. So this is our example lah. So looks here, the confidence level is 95. This what the question said. Let's say the confidence level is 95. So confidence interval is this because of what? Because if you look at this the table here, if you go to this table, standard normal distribution, if you try to find this thing 169, 169. What does it mean? I put in graph lah, easy to you. So I put in graph. What this mean lah? This is mean like this. You have something, the normal distribution like this, and then you have what we call the area of you want to put your confidence level 95%. So meaning that in between this and between this is 95%. Is 95%. Okay, 95%. Okay, 95%, and then whatever out here is 2.5% lah, 2.5%. Here is 2.5%. 2.5%. That's what does it mean by confidence level 95%. So this confidence interval, this 1.96 here, where this come is because you already know the population. This come from here, 1.96. 1 point here, you can see here this what we call this graph. You go to standard normal distribution because you're dealing with the population. 1.69, 1.96, 1.9 here, this 9, 6, and then you get around here, I think. Yeah, you get this, you get that thing. So let me make it bigger. So you get that value, 1 point, this thing, you get 0.475, 475, 475. So you can see where is the area, this thing. So that's 475. So that is basically 169 is basically that thing, that the 1.69. You have something like this. You have what? Let me put this thing. So Z at 1.69 is basically this area. You have this area, and then you have this area, and then you know this thing from the probability table is 0.475. 475 if I'm not mistaken. 169, 475, 0.475. Meaning that this correlate to 47.5%. So because you see plus minus there, so if you 47.5% times 2, you get 95 lah. You get 95%. So that's why you get this 95, because you already know. See, this 95% because you say this thing, confidence level is 95. You already confidence is 95%. That's why you straight away change with 1.96. Okay. If let's say you are doing sampling like your case here, let's say you do your sampling. So this is if you deal with population. But if you do this, if you sampling, you will get also the curve. You will also get the curve like this. You will also get the curve like this. Okay, but you cannot directly relate to what we call to the table, even though this. So you don't know. You don't know where is. You also want what we call. Basically, you also want to see where is your data lies. You want to see 95% because this is your confidence level that you put. Remember here, the confidence level you put 95. So meaning that you also want to find where is your data lies. So this, imagine this is 95 region, but this 95 region is not as same as in the Z table. So that's why you cannot ni lah. So that's why you need to sort of like correlate with the you want somehow correlate with the normal distribution graph, but you cannot, because you know from what we learned before, whatever you get is less, is not accurate enough to project to the normal distribution. So because of that, you need to find. That's why you use a T. You use T, the T value. So the T value, that's why you use T value. That's why you use, instead of using this, now you use CI equal to X plus X bar plus minus, and then you have T there. You have T, and then times with the standard error. So you have T there. You have new term here. So the T you can find from the T table lah. So you have also in the graph, in the what we call in the statistic table. Normally in statistic table you have standard normal distribution, and also you have also T. Okay, if you go to T, the T critical value of T, you see what does it mean by T. Okay, so you see T is depend on degree of freedom, the one that I said before. The higher the degree of freedom, meaning that degree of freedom relate to the sample size. Degree of freedom just simply n minus 1, your sample size minus 1. So the higher number of sample size you conduct or experiment you do, the higher the degree of freedom lah. And if you look at T, so here is the area, area in two tails. Okay, meaning that there are two tails lah. Area in two tails meaning that this lah. You have two tail. Here you this what we call tail lah. Tail. So we want our tail here. We want also to reflect this thing. So we know this is 2.5% and also 2.5%. So 2.5% times 2.5%, you get 5.0 lah. 5%. You get 5%. So this 5% equivalent to 0.05 lah. So if you look at this table, you will see that here area into tails 0.05. So if you look at this 0.05, meaning that is 95%, is the area lah, from the left hand side to tail lah. So if you look at this, the value, if you have degree of freedom 1, you get what? 12. If you have degree of freedom 2, you get 4. If you increase the degree of freedom, you look what happened. Just look at this column, this 0.5 column, this column. So you see, if I increase the degree of freedom from 12 become 2, and then go down, nearing. If you go until down, you can see at the infinity here, you get 1.96. The same degree of the same number when you do the Z, when you know the population ni lah standard deviation. You see at the end you will get 1.69. Okay, but before you have a larger T lah, larger T. But if you go until infinity, meaning that you reaching the population, you are nearing the population, this 1.69. This we say before. Where this come from? This come from the Z table. And if this thing, for example, if t nearing to infinity, then you get what we call the value will be similar to what you get in in a standard distribution table. So that is what we want lah. We want t the graph will approximate will approach normal distribution. So when you do experiment, basically what you want to do is that you have data, and then your data lies in some of the region here, whether in 95% or the other percent or whatever. So if your data lies in what we call in one region, so you can see the significance of data. For example, if your data mostly lies in here, let's say your data lies here in the middle, okay, in the middle, then we can say your data is normal lah. Your data is normal. When your data is in the region here, then your data is more or less normal with other things, other stuff. So that's why when you are at 95 here, it's not significant lah. Your data, you don't reject the null hypothesis. You accept the null hypothesis lah. So that's why. But if your data goes below that, meaning that goes far, at outliers. So let's say in here, 2.5, meaning that 5% lah. So you get like 0.05. That's why people say if you have p probability below 0.05, then your data is significantly different than the normal. So the normal here, you assume the normal, meaning that the hypothesis is the null hypothesis is accepted lah. Is accepted. But if you go here, the yellow part, is lower than 0.05. So if your data, whatever hypothesis lie here, then we can say it's significantly different than whatever in the middle here. So that's why you get significant and not significant term in what we call in DOE.